So today we'll finish up cache coherence and cover interconnects. And I promise to finish early today because I have to go to a faculty meeting. Actually, I should be there right now, but I want to tell you about interconnects, which is very exciting. OK, so you know that homework 7 is due. Well, there's no due date, but if you want the answers, we're going to provide the answers. This is homework 5 grade distribution. You guys are doing well on homeworks, but this is not going to affect your grade anyway, so this is for your benefit. Well, if you're around here, then there's some issue here. It may not have been graded, though. OK. You know that your next lab is due May 3rd, which will be fun. You'll implement the MEZE cache coherence protocol. And you know that you have an automatic extension of 7 days granted for everyone. And there are no other late days accepted. And this is what you're going to implement, which we've covered in the last lecture, right? MEZE cache coherence protocol. Final exam, we'll talk more about this. You have a question?
I want to make sure that I get this correct. So the drop dead deadline for the lab 7 is the Friday of the exam week, the 10th. Because I think on the lab write-up it was saying something about Wednesday.
Oh, that's right. Yeah, the lab write-up is wrong. Whatever I said here is right.
Okay,
So can we fix that lab write-up? If it's not already fixed. But whatever I said here is the updated version. Lab write-up and these slides are not coherent, apparently. They're not employing a good version of the MEZE protocol. OK, so this is going to be comprehensive. 3 cheat sheets will be allowed, and we will hopefully have a review session sometime, either next week or during the weekend before the exam. What do you guys prefer? During the weekend, right before the exam, or during the week? During the week will be next week. Who says weekend? Looks like weekend dominates. How about during the week? Still weekend dominates. OK. But there will be recitation sessions, which are kind of like review sessions. You can actually ask questions from the previous exams. And I would encourage you to study last year's final exam and all of the exams that you've had so far. And remember that this is 30% of your grade. So if you have to, is it 30% or 25%? Actually, I don't remember. Something around that. 25 probably, yeah. We've probably reduced the percentage and given more to the labs. OK, that should be corrected. And I will definitely take into account your improvement over the course. So if you've done really badly in the second exam, no need to worry. If you do really well in the final exam, you'll still do well, hopefully. And this is obvious, I hope. Know the previous midterm concepts by heart. And know everything by heart, right? Including whatever we'll cover today. So last lecture, we started with bottlenecks and parallel processing. So hopefully you'll know that by heart, too. We talked about multiprocessor correctness. We spent a lot of time on sequential consistency. How should the order of memory operations appear to different processors? And we talked about weaker consistency based on the downsides of sequential consistency. Right? And hopefully you remember this. Cache coherence, we've covered a lot of cache coherence. We talked about why software is not a great place to do this, or is a non-solution, at least for the hardware at least for general purpose programmers. We talked about update versus invalidate protocols. Do you actually, whenever you're writing to a shared cache block, do you update the other caches, or do you invalidate the other caches? And there are trade-offs associated with that. And you can actually come up with hybrid protocols, right? We talked about 2 major forms of cache coherence, Snoopy cache-based coherence versus directory-based, and we'll pick up on that. And we talked about the evolution of a cache coherence protocol. We started out with a simple cache coherence protocol that had 2 states, right? Valid, invalid. Whenever you were writing to a block, you would invalidate other processors' blocks. Right? And then we developed modified shared invalid 3-state protocol, and then 4 states, MEZE. And then we added the owner state into the MEZE protocol. Hopefully you remember, right? Today we'll wrap up cache coherence and talk about interconnection networks, which are actually tightly related in designing a scalable multiprocessor system. And you know these readings. OK, we've talked about this. This is the MEZE state machine, just to jog your memory. And this is actually implemented, well, something like this is implemented in many cache coherent multiprocessors today. And Intel Pentium Pro implemented this, basically, which is very similar to what you have in the lab. The problem with MEZE, we discussed this. I'm going to go through this relatively fast. The shared state requires the data to be clean, which means that if a processor is the only processor that has that data block, it doesn't know this, right? You need to write the block to, well, I guess we've, wait a second, this is, yeah, you need to write the block to memory when bus read happens when the block is in modified state. Well, this is another problem. This is not the problem I was going to discuss, but basically, yeah, basically you need to, well, I guess I was talking about the problem with MSI. The problem with MSI is if you don't have MEZE, if you don't have this, the problem is in your shared state, you do not know whether you're the only owner or you do not know if there's some other owner. So you cannot just write to a block if it's in shared state, right? If you have the MSI protocol. So this protocol, MEZE, improves upon that by dividing the shared state into shared clean versus exclusive clean. Now that the processor knows if it has the data exclusively by itself. And by having this knowledge, if the block is in this state, the processor can silently write to the block without notifying anyone, right? That's the improvement MEZE, this 4-state protocol, had over the 3-state protocol, right? MSI. Now you know you're the only owner. You're the only cache that has this data. You can write to it without informing anyone. So that enables invalidation traffic to be 0 if the copy is the only copy in the system, right, whenever you're writing to it. And this actually buys a lot of performance. So going from MSI to MEZE buys a lot of performance. That's why MEZE is a common protocol that's implemented. Now this also has a problem, which we've discussed. I'm not going to go through this. I'm going to go through this quickly. But this shared state requires the data to be clean, this shared state. So all caches that have the block have the up-to-date copy, and so does the memory. Which means that when you need to write the block to memory, when a bus read happens, you need to write the block to memory when the block is in modified state, so that you can go to the shared state, right? So the problem, why is this a problem? Because memory can be updated unnecessarily, right? You may be writing the block to memory, and then some other processor may write to the block while it's cached, after it's cached. You want to avoid that. So how do you improve upon that? Basically, first, do not transition from a modified to shared state on a bus read. You can invalidate the copy and supply the modified block to the requesting processor. Right? So when a bus read comes, well, yeah, here it is. When a bus read comes, when you're in the modified state, you don't transition to the shared state, but you transition to the invalid state. And you supply the modified data to some other processor, and that other processor who was in invalid state goes to modified state. Right? That's an update-based protocol. You're kind of updating some other processor's state. Right? That way you can save memory bandwidth. So that gets rid of the second problem with MEZE. That's one way of getting rid of the problem. The other way of getting rid of this problem is you can transition from modified to shared state, but designate one cache block as the owner. Right? Now, multiple cache blocks can be in shared state, but one of them is the owner of the data. And that's going to be the cache that's going to write the block back when the block is evicted. Which means that the shared state now means shared and potentially dirty. This is one version of the MEZE protocol. You have an owner. So it's 5 states, basically. Because you need to designate an owner in this case. You don't want all of the caches to write back the block. Right? Because now multiple caches have a modified copy that is shared. OK. So this is just an example of, and you can improve upon this too. The protocol, basically the higher level point is, the protocol can be optimized with more states and more transitions, and maybe even prediction mechanisms. Maybe you decide whether you transition from modified to shared, or whether you transition to modified to invalid based on a prediction you make. Right? If the prediction is that that other processor is going to use the modified block, maybe you go from modified to invalid and supply the data to the other processor. If the prediction is that you should write back the block to memory, then you go from modified to shared. So if you do these optimizations, you can now reduce unnecessary invalidates and transfers of blocks. Right? Of course, there's a downside with all of these optimizations. With more states and optimizations, now you have a protocol that's more difficult to design and verify. actually, this leads to more cases to take care of, lots of race conditions. You'll see this in your lab when you implement the MEZE cache coherence protocol. There can be cases where you need to decide which processor actually gets to get the block, right? If you don't have the states correct, if you don't have the state transitions correctly, you may get the wrong data. So you'll see this firsthand when you implement the protocol. Actually, your job is easy because in your case, we'll assume a shared bus, right? But in many systems today, cache coherence is many systems today are actually distributed, right? So what you have is I won't have this nicely, but actually I guess we could have this nicely by making this a ring, right? You have a ring of processors. There is no shared bus. The processor caches are connected via a ring, and maybe it's a doubly, maybe it's a multi-directional ring, right? In this case, when a processor does a bus read, that's not observed, right, by everyone. And the question is, how do you actually implement a protocol like this on a ring? And we will see that something simplifies this, right, which is the directory-based coherence. Okay? So your task will be easy, but real systems, keep in mind that will be much more difficult. And this will run into race conditions even more. Because now, when one processor is writing and another processor is reading from a cache block, those need to be serialized somewhere. And a bus serializes nicely, but this ring doesn't serialize it, so you need to have a serialization point. Right? Okay. And also, if you add more states and optimizations, these provide diminishing returns. Going from a protocol valid to invalid to MSI buys you a lot of performance. Going from MSI to MEZE buys you less performance. Going from MEZE to MOEZE buys you even less performance. MOEZE to your own protocol will probably buy you less performance, although that's not always the case, right? Maybe you come up with a very good prediction algorithm that gets the best of many of these. But this is usually the case. Okay, let's revisit these two cache coherence methods. We've talked about Snoopy bus and directory, and we've talked about the MEZE. Actually, MEZE protocol we discussed it in the context of a Snoopy bus, but you could actually implement it on a directory as well. Right? This is really a higher level protocol. Whether or not you have a Snoopy bus or directory just changes the implementation of the protocol. So we discussed MEZE in the context of Snoopy bus, but we'll take a look at how that can be done in the context of directory also. Okay, what's the difference between these two protocols? Basically, Snoopy bus, you have caches connected to a single point of serialization for all requests. All requests are serialized. This makes the protocol implementation easier because now everybody observes the same actions from different processors. Right? Directory, instead of having a single point of serialization for all requests, you have a single point of serialization per block. Right? And this could be distributed among the nodes. For example, I've already given this to you last time, but blocks 0 through 1 million can have a directory that's here. 1 million to 2 million can have it here, and then dot, dot, dot. Now you don't need to serialize with a single bus. Anybody who requests a block that's at address 1 million sends a message to the directory that's at this node. And this node serializes those requests. This node knows which caches contain this particular cache block that starts at address 1 million. Right? So if you look at this, this is more scalable, right? Because you have a single point of serialization per block. Whenever coherence transactions are happening for this block on this node, other coherence transactions can be happening for some other block on another node. Right? These blocks have nothing to do with each other. Their coherence transactions should not really be serialized. Whereas if you have a Snoopy bus, you really have a serialization. Right? So this is fundamentally more scalable way of designing cache coherence. Of course, it's as scalable as the interconnect you can build. That's why we're going to cover interconnects next. Okay? Any questions? So we'll go back to upsides and downsides. Actually, we will go to upsides and downsides here. But if you look at there must be a downside to there must be an upside to this also, right? What is the upside to Snoopy bus?
Simple.
Simple is always a good upside. That's right. Simple is a good upside. It's much simpler, right? It's simpler to reason about. Although directory is not too bad, except there may be many transactions going on at the same time. What is the other upside in terms of performance? Is there some upside? If you don't want a scalable system, let's say. There's no indirection, right? Whenever you're writing or reading a block, you just send a message saying, I'm reading this block. And everybody sees that. You don't need to go to the directory and say, directory, I want to read this block. Tell me if I can do it. Right? The directory calls that indirection, which adds latency to the system. So if we want to evaluate the advantages and disadvantages, Snoopy cache, critical path is short. You have a miss, it's basically a bus transaction to memory, and everybody sees that bus transaction. Right? No need to go to the directory. And global serialization is easy because bus provides this already. Although for cache coherence, you don't need global serialization across all different blocks, right? Because cache coherence is really about the state of a single memory address, single cache block. You really don't need serialization across all memory requests. That's why a directory works, right? You have serialization for a single block. You really need to keep a single block coherent. That's the big difference between coherence and sequential consistency or consistency methods. Coherence is about keeping the data of a cache block, of a single cache block, actually a single word it could be, it doesn't have to be at the cache block level, coherent across all processors. All processors see a coherent state for that data. Whereas consistency, which we've discussed earlier, is totally different. This is basically all about memory ordering, right? How do the different processors see the ordering of operations to potentially different blocks in the system? Right? So sequential consistency is all about all processors seeing the same total global order of accesses to all possible blocks. Right? So this is about a single block. This is about every access to any block. Right? This is about the coherence of data. This is about the ordering of memory accesses. These are very different concepts, so keep this in mind. A bus actually helps both. A bus basically enables a serialization point for all blocks here, but it's too strong, right? You don't really need the serialization for all blocks here. You may need the serialization for all blocks in sequential consistency. Right? When you provide a sequential consistency, you do want all processors to all other processors' actions in the same order. And a bus enables that nicely. A bus enables coherence nicely too, but it's not necessarily needed. Now you can imagine how you actually do sequential consistency on a system like this, right? Well, I'll let you figure that out. OK, so this is simple. This is your advantage, appears as the third, looks like. You adapt bus-based unit processors easily to this. The downside is it relies on broadcast messages to be seen by all caches, right? Which means that you have a single point of serialization, which is the bus, which is not scalable. Although you can implement you can implement a version of snooping without the bus, and I'll let you think about that also. We're not going to go into that. If you want to learn more, you can take the next courses. Directory, we've already covered the downside. It adds indirection to the critical path, right? You cannot just do request, and request is seen by everybody else. Request needs to go to the directory, and then directory needs to access memory or other processors, and then supply things back. And it also requires extra storage space to track share sets, right? So you don't need this in the Snoopy cache. Snoopy cache, you only need to keep track of the blocks that are present in the caches, right? Whereas with a directory, you need to keep track of the status of every possible block in memory, right? So it requires more state. And you can calculate that state. The upside is it can actually be approximate, right? And in this case, your false positives may be OK. If the directory doesn't exactly know who has the block, as long as it thinks of a superset of processors, as long as it keeps track of the processors that have the block, it may think that some other processors also have the block, But that's okay, right? The directory can send a message to a processor, and say that invalidate this block. If the processor doesn't have that block, when it receives that message, it basically drops that message, right? So it's okay to be conservative in keeping track of which processors have the block. So it can be approximate. Actually, Bloom filters can work nicely with this kind of structure, right? Maybe you don't need a bit vector, as we discussed in the last lecture, to keep track of which processor has the block. You may actually use a Bloom filter. But then the question is, how do you actually send a message to get the data back? You somehow need to broadcast to all of those processors that map to that Bloom filter. Yes?
Doesn't that just degenerate into a bus, like a common share bus?
So that's not necessarily a bus, but maybe a broadcast. You're thinking,
right.
yeah, that's right. Maybe depends on how you implement it. Right? Maybe it degenerates into something like a multicast. You send to many processors that you think have the block. Please send me the block, and so only one of them has the block, right? So it may not be as bad as a full broadcast. Okay, and we'll get to this. We'll cover this briefly, but you can think that this could be actually approximate, so you can reduce the storage space. With a directory, actually, protocols and race conditions are more complex, and I'll cover this briefly because of this indirection, basically. You do not have the single point of serialization. Single point of serialization reduces the race conditions that you need to handle. The big upside of a directory is it's exactly as scalable as the interconnect and the directory storage. So as long as you can scale the interconnect, as long as you can scale the storage of your directory in a way like this, you can scale up your system, which is much more scalable than a bus. And we will see that in the next part of the lecture. Any questions? So Intel Pentium Pro actually had the Snoopy cache, bus-based Snoopy cache. But many systems today have directory-based coherence protocols also. A lot of AMD systems, for example, have directory-based coherence protocols. Mainly because we would like to scale the system, right? We're putting hundreds of cores on chip. How do you actually scale the system? Okay, let's revisit directory-based cache coherence. I'm not going to go over this in a lot of detail. And you remember how the directory operates. This is a slide that you've seen. Basically, you have 1 bit per block. For each block, you have 1 bit per cache that can contain the block. In this case, if you have 4 processors, you have 4 bits, and you have an additional bit, which is the exclusive bit. And you remember the purpose of the exclusive bit, right? That tells that this block is present only in one processor's copy, and that processor can write to it without notifying anyone. Which means that you need to have this bit within the processor's cache also, so that that processor knows it has the only copy. This is the same bit actually in the MEZE protocol, right? It is that exclusive bit. Directory needs to know about it. And you can actually think about implementing MEZE protocol using a directory-based coherence. Okay, you remember this. So these are actually likely required when scaling past the capacity of a single bus. This is actually a little bit strong. It's not really required. You could still employ a Snoopy-based protocol, but it needs to be more complex. This is distributed. Fundamentally, directory-based protocols are more distributed, but coherence still requires a single point of serialization for write serialization. Remember, you need to serialize the writes to a block. The big upside is serialization location can be different for every block. It could, for example, be striped across nodes. Here, I didn't stripe it across nodes, but cache block 0, all the way up to all of the cache blocks that are contained within the memory space 0 through 1 million are in this particular directory here. This is directory for 0. This is directory 1. But you can map the cache blocks in different ways, right? Cache block 0 can be here. 1 can be here, 2 can be here, 3 can be here, dot, dot, dot. And then you wrap around, maybe cache block 16 can be here, dot, dot, dot. How you map the cache blocks to the directory, actually, and maybe the memory here, depends how much contention you will get in the entire system, right? For example, if there's a hot cache block here, everybody requests that. Now you have a lot of contention in the network, in memory. So that mapping, and we've seen the mapping to memory, this is essentially the mapping to memory, right? You're mapping which cache blocks are in which directory, and usually your directory if a cache block is in this particular directory, it's also in this memory, right? Probably doesn't make sense to put the cache block in that memory and directory here. Does that make sense? Okay. Okay. Now we can reason about the protocol for a single block. Right? For a single block, you have a server, which is the node of the directory here. Cache block 0, for example, is contained in this node. And you can have many clients. Clients are these different private caches that may want that block, that may want to write to the block or read from the block. Right? So it's really a server-client protocol that you have. Whenever a client wants the block, it requests to the server, the directory node, I want the block. Basically, directory receives these read and read exclusive requests and sends the invalidation requests. And invalidation can be explicit, right, as opposed to Snoopy buses. Right. Basically, you need invalidation messages. Right. Whereas in a Snoopy bus, whenever you see a read exclusive request, you can transition from a state to the invalid state. Right. So that's implicit. Whereas here you need explicit invalidation messages. So you can actually optimize this protocol quite a bit also, and I'm not going to cover that. And if you want to learn more about that, that's the next course. Basically, you can. I'll let you think about how you can implement a MEZE protocol using these server, this kind of server and client-based substrate. Right? You can actually implement the MEZE protocol on top of a directory. And I'll let you think about that. One thing we briefly covered is the data structures. Like, what does a directory actually store? The key operation to support is a set inclusion test, right? Basically, which processors can have this block, right? That's the key operation, really. And that key operation needs to be, let's assume that this is your directory node. For each cache block, and it could be actually for each word in memory. Let's talk about that. Let's put this on our stack. But the granularity of coherence is another issue. I'll get back to that. But basically, for each cache block, do you have a full bit vector of processors that can potentially contain this block? What if you want to scale up your system? What if you want to have 1,000 processors? For each cache block, do you have 1,000 bits? That's a lot of overhead, right? But if you want to have 10,000 processors, well, 10,000 bits is a lot again. So that's why making this storage structure scalable is an important problem. And you can do several things for this, right? False positives are OK. That's the first observation. Basically, you really want to know which caches may contain a copy of the block. And as long as you know that, you send a bunch of invalidation messages to those caches that may contain the block. And when they receive the invalidation message, and if they do not have the block, they'll just ignore it. But of course, false positive rate now determines performance, right? Because you would be sending a bunch of invalidation messages unnecessarily. So there's a trade-off. You're reducing the space of the directory, but you're increasing the number of invalidation messages you send. Most accurate, obviously, is a full bit vector. But you can have compressed representation. You can actually compress these bit vectors, and there have been processors that employed that. You can actually have linked lists, right? Maybe usually only 2 or 3 processors contain this block. So what if you just have a linked list and you store it somewhere? Maybe you store it in main memory. As long as you don't make it shared, right? As long as different processors don't write to it, because now you have a chicken and the egg problem. You have a recursive directory problem if you do that. And balloon filters are also possible. But we're not going to go into that. A lot of the existing systems try to optimize the directory space, although none of them really went up to 10,000 processors, I believe. Well, actually, that's not exactly true. There have been processors that were more SIMD-like processors that had 65,000 processors, 64K. Connection Machine, for example. The Connection Machine 5 had 65,000 processors. But they were more lockstep. So they were SIMD processors. OK. So what are the basic operations? Basically, you can follow the semantics of a Snoop-based system. Basically, you can implement something like a MEZE protocol, but with explicit request-reply messages. The key is explicit messages, whereas implicit bus-based serialization. directory receives these different requests, read exclusive, or upgrade requests, and sends invalidation and downgrade messages to the shares if needed. And it forwards requests to memory if needed. So if the data is actually in memory, the directory has knowledge of that, and it can get the data from memory and supply it to anyone. It replies to the requester and updates the state within the directory. Now your protocol design is very flexible, right? You can actually do many different optimizations. The directory may speculatively send requests to some caches telling them to supply the data directly to some other processor. And we'll see an example of this. So you can do cache-to-cache transfers. Let's take an example of that. Let's say you have processor 0, and this is the home of the location, the cache block that this processor is trying to access. So the processor 0 sends a read request to the directory that houses that cache block. That's called the home node of the block. Basically, home node of the block is the node that contains the directory entry associated with that block. And somehow that needs to be deterministic, right? The processor, when it generates the address, it needs to know which home node to send the request to. And the home node can simply reply with the data. And it can say, now you can have the data exclusively, or you can have the data in a shared way if some other processor has it. Now, the home node can actually, the directory can also say this. The directory figures out that the data is actually at a processor that is closer. So let's say this is processor 0 and processor 1. And the directory for the node, that's the block that's accessed is far away. Processor 0 says, directory, I want this block, cache block A. Directory figures out that actually P1 has it, right? And directory simply can send a message to P1 telling P1, P0 requested this block, so send that block A that I know you have to P0 directly. Instead of me, even though the block here, block A, may be the same version as block A in memory. So it may be not in the exclusive state. The directory might tell processor 1, transfer block A directly to the cache of processor 0, because you're much closer. And I don't want to access my memory, because my memory access will take much longer, right? Whereas this cache-to-cache transfer it can take much shorter. So you can do this kind of optimization, because the directory knows where the nodes are located, or it can know where the nodes are located. And it can optimize the latency to transfer cache blocks when processor 0 requests it. Now that's an optimization, and this could work. Now the downside is you can run into race conditions, right, if you do this. What if processor 1 at the same time is writing back this block? Or at the same time is evicting the block? Well, it cannot write back, I guess, in this case. Well, it could happen also if it's in a modified state. What if it's evicting this block? It will receive a message, and when it gets the message, it doesn't have the block in its cache. So now your protocol design is more complex. This processor needs to respond back to the directory saying that, oh, I don't have this block anymore. While you were sending me the message to send this block to processor 1, I was actually sending you a message to tell you that I'm actually getting rid of this block from my cache. So you need to design the protocol such that you handle these race conditions. OK, there's another example here. Let's say this processor 0 wants to exclusively request a cache block. That's block A. It sends a message to the directory. Now, the directory figures out that actually some other block has this some other cache has this block in exclusive state. So it sends an invalidation request to the owner. And the owner basically responds back, sends a revision. Revision, this is terminology in directory-based protocols in the paper you may be in the chapter you're reading. And now, because this owner has the only copy of the block, it's the exclusive copy, it sends back to the directory the data such that the directory can write it back to memory. And the owner at the same time can send the data to processor 0. Processor 0 wants it to be an exclusive state, so it really needed that data, up-to-date data, so that it's going to write to it probably, because that's why you want the data, you want the block to be in exclusive state. The owner, while it's updating the directory, it can also send a message to P0. Now we run into different race conditions here also, right? So you can optimize the protocol much more easily if you have a request-reply-based protocol, a request-reply-based substrate. Okay, contention resolution. This is another example. Let's say two processors are requesting the same block at the same time. They send a read exclusive request to the same block to the home node, and home node decides to acknowledge only one of the processors. You cannot give the same block in exclusive state to two processors, right? Because only one of them should be writing to it. That's the write serialization requirement. You will need to serialize the writes. Otherwise, you'll get an inconsistent state in the block. And the home node now you have a choice actually. What does the home node do to processor 1? It can say, oh, I cannot give it to you right now, so request it again. That's called a negative acknowledgement, NAC. It can NAC the home node. But there's another possibility you have. Maybe home node can buffer these requests, right? If you have enough buffering, the home node can buffer the request of processor 1 and wait until processor 0 is done with it. Okay? So now processor 0 is happy, processor 1 is upset. After a while, processor 1 retries and asks for the request, read exclusive request. Now the home node invalidates processor 0. Processor 0 sends the dirty data both to the directory and processor 1. Okay? Well, these are some cases. Now processor 1 is happy, I guess. Okay. So contention resolution actually, this could happen a lot, especially if you have a contended data, right? Let's say you've designed a multi-threaded program, you have a critical section, and you have a lock, and everybody wants the lock. Or a lot of threads reach the barrier at the same time. That's what's happening here, right? Basically, a lot of processors want to write to the lock because they want to get that lock. So you can have this contention. This could also happen on the data as well, but or condition variables. Okay, so you need to somehow escape these race conditions by NACking request to busy entries, and the original requester retries. Or you can queue the requests and grant them in sequence. Then the question is, how big should your queue be? Right? Or you can have a combination of both. Right? Fairness is an issue. So how do you actually provide fairness to these different processors that request a block? Which requester should be preferred in a conflict? Right? There are performance issues here also, right? Because maybe there's a far away requester and there's a close by requester. Which one do you service first to improve performance? I'm not going to give you answers to this, but there's a lot of research as well as design that has gone into this. Interconnect delivery order and the distance both matter for fairness, right? That's what I mentioned. Which processor is far away, which processor is close by. You can actually have ping-ponging, which means that you could have these invalidations happening as a chain, and the data, the block traveling from one processor's cache to another processor's cache. That problem you cannot actually solve easily at the protocol level, because that problem is because of something higher, right? Which means that you've written your program such that this ping-ponging happens. So maybe you need to redesign your data structures, locks. You need to rethink your locks. If everybody is requesting the lock at the same time, and that lock is contended, maybe you want to reduce that contention. Okay, we're not going to go into that right now. I promised that I would go into granularity of coherence. I'll just pose some questions. We've so far thought that granularity of cache coherence is at the cache block granularity, right? But this doesn't have to be the case. You could have granularity at the word. You can provide coherence at the word granularity. For each word, you keep track of the sharing state. Of course, the downside now is this is higher overhead, right? For every word, you need to have a share set if you have a directory. Or if you have a MEZE protocol, you don't, again, have to have it at the cache block level. You can have a sectored cache, right? For each sub-block, you can keep track of the coherence state. So the upside, what is the upside of doing it at the, Obviously, the upside of doing it at a larger granularity or coarser granularity, which is the cache block granularity, the upside is the hardware cost is lower, right? You need to keep track of less state. What is the upside of doing it at a finer granularity? Keeping coherence at a word granularity rather than a cache block granularity. There must be an upside. Yes?
Might have less state transitions.
Yes, a block may have fewer invalidations, for example, right? There's a word for that, actually. You may have read it in one of the papers that you're reading. No? So as you reduce the granularity of coherence, if you keep coherence at a finer granularity, at a word granularity, you reduce something called false sharing, right? False sharing happens when two processors need the same cache block, and they need to, maybe they write to it, for example, and they need to invalidate that cache block, even though they're not really sharing data. They're sharing the cache block, but they're really not sharing the words within the cache block, right? So a cache block contains a number of words, let's say 4 words in this case. This processor is writing to this word, and this other processor is reading from this word. These have nothing to do with each other, right? They just happen to be in the same cache block. If you keep coherence at a cache block granularity, well, you have no idea. You don't. Basically, you just need to transfer the cache block. Basically, this is now you have false sharing, because when a processor writes to this part of the cache block, the other processor's cache needs to be invalidated, right? That's the idea of false sharing. So as you reduce the granularity, you will reduce this false sharing, because if you kept the granularity at the word level, whenever this processor writes to this other part of the cache block, that block doesn't need to be invalidated in this other processor's cache. That's the upside of finer granularity. Now you can make the granularity even coarser, right? That reduces your overhead. You can make the granularity page granularity, perhaps, right? Now you don't really need to keep track of coherence at the cache block granularity. Your state is smaller, but now your false sharing increases, right? So as you increase the granularity of coherence, your false sharing increases, but your hardware overhead decreases. Okay? So how can you reduce false sharing? Well, maybe you allocate your data nicely, such that potentially contended words don't go into the same cache blocks. And that's one optimization you can do, if you know those words. OK. How do you actually scale the directory? I'll leave you with some questions, actually. How large is the directory? We already talked about it. You can do the calculations, perhaps. This depends on how you actually store the shares set in your directory. And you can actually you can optimize this to reduce the size. But size of the directory is an issue as you scale the memory size, right? As well as the processor size, because the size of the directory increases with the size of your memory, as well as the size of the number of processors that you have in the system. How can we reduce the access latency to the directory? That's another issue, right? Let's say you have some blocks that are cached, and the directory is far away. Do you always keep going to the directory? Well, whenever you have a latency problem, maybe you cache the directory as well, right? And existing systems have directory caches. They cache the directories in different nodes. That way you can reduce the access latency. How can we scale the system to thousands of nodes? Well, I guess this affects both of them, and I'll let you think about these questions. One of the things that affects scalability significantly is the interconnect. I think I'll just jump to it, unless you guys want to take a quick break. Who wants a break? No one. OK, everybody wants to finish early today. So the scalability of the system is not only determined by your directory, right? The directory size as well as access latency is one thing, but it's also very tightly coupled to the interconnect that you have. And we'll talk about the interconnect. This is going to be relatively basic, and I'll go relatively quickly. But if you're interested in this, this is going to be the next course. So what is an interconnect, first of all? Basically, the goal of the interconnect is to connect components such that they can communicate with each other. If there's no communication, there's no point to interconnect these different processors, right? But we're designing these processors such that they can communicate with each other to solve a problem. There are many examples of this. You can connect processors to processors, processors to memories or banks, processors to caches, caches and caches, and I/O devices. And we're going to abstract it with this kind of interconnection network here. And you have some network interface controller, I guess. So this is the same thing as a higher level network as well, but we're going to do it for multiprocessors. So internet is one type of interconnection network. And you could actually potentially communicate, do a cache coherence on the internet too, right? If you think of the entire internet as a global shared memory, if you can supply that address space, you need to keep it coherent, right? But that's not the way internet operates, at least not today. Okay, so why is it important? It affects the scalability of the system, and hopefully it's obvious by now. It affects its performance and energy efficiency also. How large of a system can you build? What is the scalability? More concretely, how large of a system can you build? And how easily can you add more processors also? That's also important for the scalability of a system. How fast can processors, cache, and memory communicate with an interconnect? And how long are the latencies to memory, or latencies to do this cache-to-cache transfer? And how much energy is spent on communication? These are all dictated by the interconnect. There are several properties of an interconnect. One important one, and the one which we will spend the most time on, is the topology. Basically, what does this look like? Second is routing. How do you actually route the messages? And there should be algorithms for that. And the third big one, which are actually you could consider these two separate ones, but they're tightly integrated with each other. Buffering. Where do you have the buffers? Or do you have even buffers? And how do you do the flow control? When your buffers are full, how do you ensure that they're not oversubscribed? How do you ensure that you don't lose messages? So topology specifies the way switches or routers are wired. Basically, it affects pretty much everything. It affects your routing, reliability, throughput, latency. How easily can you build this? And we'll see examples of that in more detail. Routing, how does a message get from its source to the destination? Which path does it take? What is the algorithm for that? And this could be static or adaptive, and we'll cover very briefly some different algorithms. Buffering and control flow, what do we store within the network? Do we store packets, parts of packets? Do you divide messages into smaller messages? Do we send the entire cache block, for example? Or do we send pieces of it? Or do we send something bigger? And how do we throttle during oversubscription? Whenever your buffer is full, how is that communicated to the previous router? And this is also tightly coupled with the routing strategy. And you can think about that. Actually, all of these are tightly coupled, but buffering and flow control are tightly coupled with the routing strategy more than the other one. So there are many, many topologies that have been proposed, and there's no way we're going to go over all of these. Bus is the simplest. We'll talk about that. You can have point-to-point connections, crossbars, rings, trees, omega networks, hypercubes, meshes, butterflies, tori, and more. I guess there are dragonflies also. And you can figure that out on your own. How do you evaluate this? Well, these differ in many different metrics. But one important metric, there are three important metrics. One is cost, as always. The other is latency. What are the latency characteristics in terms of hops or nanoseconds? And what is the contention? How much congestion is there in the interconnect because of the topology? And there are many others obviously exist. Energy, bandwidth, and overall system performance. But we'll talk mainly about these three when we evaluate the interconnect topologies. The bus is an obvious one, right? You have a bunch of nodes, in this case 8. Let's think about these as processors and caches. And they're connected via a bus to memory. This is another example. These are not the same thing, actually. You have these processors and caches that are connected via bus to different memory banks or different memory modules. The upside of this is very simple. It's easy to reason about, right? It's cost effective for a small number of nodes. And it's easy to implement coherence, right? You can have snooping and serialization. And it's easy to satisfy, which I don't have it here, but it's easy to satisfy, more easy to satisfy consistency. Because memory is a switch, right, with sequential consistency. Now, the switch is the bus, right? Whichever processor gets connected to the bus at any given time gets to submit its request in that global order. Okay. The downside is, I guess we've already talked about this, but this is not scalable to a large number of nodes because you have limited bandwidth, right? When this processor wants to transfer something from memory, it needs to wait for this other processor to transfer something from memory. If two processors want to access memory concurrently, well, too bad, they're going to be serialized, right? Because there's only one physical substrate. You can pipeline the bus, but it's still serialized. The other thing is, as you keep adding more processors, you'll have more electrical loading on this bus, which means that you cannot run it at as a high frequency as you could with smaller number of processors. So that's another reason why it's not scalable. First is contention. You get a lot of contention. When there are multiple transmitters, they cannot transmit at the same time. And the second is reduced frequency due to electrical loading. So we want more scalable topologies if you want to go beyond 16 nodes or so. Even 16 nodes is actually stretching it with a bus. The exact opposite end, you have point-to-point connections. Basically, every node is connected to every other. So 0 is connected to every other, and 1 is connected to every other. And you can keep adding this. It's a lot of fun. So this is your topology. It's beautiful also, right? On the exact opposite end. It has the lowest contention and potentially the lowest latency. Not necessarily, because how do you actually implement this, right? And it's ideal if cost and latency is not an issue, right? Ideal in terms of the number of hops that you need to send messages, because you don't have contention, right? With one hop, you can get from node 0 to node 4. The downside is highest cost, right? You have n connection port per node, where n is the number of processors, order of n. It's actually n minus 1 connections, right? Specifically. And you have order of n square links. And because of this reason, it's actually not scalable. So bus is not scalable for a very different reason. This is not scalable for cost as well as latency reasons. And how do you actually lay this out on chip? Right. That's another, or on a, even on a system that does not have the processors on the same chip. Right. If you want to build tens of thousands of processors, you need to somehow wire these processors, right? If they're not on chip, they need to be wired somehow, so you need to still write the wires. Actually, if you look at the supercomputers are usually multiprocessors that have hundreds or thousands of processors together. They're wired together with these big wires, real wires. And people go and wire one processor to the other one using cables. Right? And your interconnect determines the complexity of those cables. What if you wire one to the wrong one? Now your protocol doesn't work. Right? And this has happened in some of those supercomputers. You can actually see the images of these top 500. If you go to top 500 webpage, this is a competition of who can build the fastest supercomputer in the world. And if you look at the pictures of those processors, they have very, very complicated cabling that happens within a big room. And that cabling is because of this interconnect. OK, so this is not scalable. Crossbar is an attempt to get the benefits of point-to-point connections. Basically, every node is connected to every other, except one can be used, only one can be using the connection at any given time. So here, every node is connected, has its own connection to every other node. Whereas with a crossbar, only one of them. Still, every node is connected to every other, but they're sharing the connection. For example, if node 7 wants to communicate with node 0, it can directly through this crossbar. But if node 6 is also communicating with node 0, now you have some contention. You need to do some arbitration. Right? Now this enables concurrent sending requests to non-conflicting destinations. So if node 7 is connecting with node 6 here, sending something to node 6, node 0 can be sending something to node 5. So you can have this parallelism within the crossbar. And this is also good for a small number of nodes. It is low latency and high throughput compared to a bus. The downside is still expensive, right? It has O(n) square cost. And again, because of this, it's not as scalable. Of course, scalability also depends on your design point, right? So I call it not scalable, but this is not scalable if you want to build tens of thousands of processors. You can think of these as processors and memory banks also. If you have thousands of processors and thousands of memory banks, how do you connect them? And it's actually difficult to arbitrate as n increases, right? If you look at this, it's not, this mux somehow needs to be controlled. And how do you control that mux? In fact, you could argue that this may be easier to control, right? If you have point-to-point connections. You don't have that mux. Okay, this is actually implemented in core-to-cache bank networks in IBM systems, Sun systems, and many other systems today. And we'll see a picture of that, I think. So this is another crossbar design. This is a more detailed view of the design. Basically, you have these switches that connect the nodes to the shared line to the destination node. Then the question is, how do you actually connect these nodes? We'll get to that. How do you actually arbitrate? When node 0 is transferring, when node 0 wants this line to communicate, well, let's take node 1. When node 0 wants this line to communicate with node 1 or memory 1, it needs to arbitrate with every other potential contender. So if you look at Sun UltraSpark, it has something like that. Basically, it has a bunch of cores, and it has a bunch of cache banks. And this is the crossbar that connects all of the cores to bank 0. This is their crossbar. Basically, you have 8 cores and 8 L2 banks. And the crossbar requires a 4th stage pipeline, which is you need to request, and the requests arbitrate with each other. And the arbiter selects which one can go on this line. And in the next stage, the transmission happens. So there is latency added to it, right? It's not as simple as a bus. And there's a 2 deep queue for each source destination pair to hold data transfer requests. And these are the queues. Again, I'm not going into the detail, but this is a simple concept. And it could be implemented this way. Actually, I believe this crossbar was 8 to 9 crossbar. Yeah, that's right. There's a network unit also in Sun Niagara. Each core can communicate with either 8 of the banks or the network unit, network control unit. If you're going off chip, right? Okay. So this is actually a bufferless crossbar. The slide says buffered crossbar, but we're going to build it. So you can have a bufferless crossbar. The problem with a bufferless crossbar is now you need to somehow arbitrate before you send the data. The alternative is to have buffers here. Basically, when you send the data, you put it into a buffer, and these buffers somehow arbitrate with each other. And there's an arbiter that determines which buffer can actually send the data through this line. This is actually a more fundamental design choice in any network. Do you design buffers, or do you have buffers in the network, or do you not have buffers in the network? In this bufferless case, the upside is kind of obvious, right? No buffers. They don't consume energy. In this buffered case, there are buffers. Now you need to arbitrate. There's complexity. But in the bufferless case, you need to arbitrate also, right? You still need to ensure that only one of them can transmit. So that didn't go away. But there are buffers, which is complexity. Now you need to ensure that these buffers are not overflowing. So whenever this processor sends a request to any buffer, there needs to be a flow control mechanism that says, oh, you cannot send it anymore because I'm full. Right? That's called the flow control mechanism. The upside of buffers here is now the network can sustain a lot more packets. Right? Now, how many packets you can store in the network is decided by how much buffering you have in the network, which means that you have more bandwidth in the network. This node can send a request and maybe forget about it. Depends on the high-level protocol, right? It can send a prefetch request and forget about it. It doesn't need to wait for the network. Okay? So upside is simpler arbitration and scheduling. And you can have efficient support for variable size packets, which I didn't go into, but you can think about that here. Now you require n² buffers. That's the downside. And we'll get back to this actually on a general network. Okay, can we get lower cost than a crossbar? Crossbar is still costly if you want to design if you want to connect 10,000 processors to 10,000 memory banks, which is what people tried to do when they actually designed these supercomputers, and they still try to do, right? If you want to have 10,000 cores on a chip, which is the same problem as a supercomputer, yet still have low contention. And I guess the answer is yes. But how do you do that? This is how multi-stage networks were developed. You want to get the benefits of a crossbar, or most of the benefits of a crossbar at a fraction of the cost. What is the idea of a multi-stage network? Basically, you have an indirect network with multiple layers of switches between terminals and nodes. So if you look at this, these are the sources, and these are the potential destinations. Instead of directly connecting the source and the destination, which a bus, crossbar, or point-to-point interconnect does, now you have indirect connections. You have these switches or routers that do nothing but route data. Actually, they could do some other things. We may get to that. But that do nothing, but their sole purpose is to route data. They're just switches. They're not processors, they're not memories, just switches. That's why this is indirect. If 000 wants to communicate with 110, it goes through this switch. Well, there must be a way, right? Well, I guess not. I guess not with the Omega network. Okay, yeah, there is a way, right? You go through here, you go through here, and you go through here. That's how you need to set up the switches. Right? Basically, with the Omega network, you can communicate with from any source to any destination. Some other networks, you may not be able to. Now that reduces your flexibility. Right? But we're going to be concerned with the networks that where you can communicate. Now, if you look at the cost of this, this is all n log n. Really. It's not n² anymore. And you can think about this. And the latency is really the log n. If you look at this, log n in the number of nodes, right? We have 8 nodes here, and we have 1, 2, 3 stages. And if you have 16 nodes, you'll have 4 stages. If you have 32 nodes, you'll have 5 stages. Right? That's why it's log n. And you can convince yourself by thinking about it a little bit. And there are many variations of these indirect or logarithmic. It's also called logarithmic networks. Omega is one. We're going to look at one other one, which is a delta network. But there are a bunch of other ones which differ basically in the connections that they have in these routers. How many inputs they take, how many outputs they have, and what are the connections like. Make sense? Okay. Well, I guess one issue with these networks is if you can have contention now, right? That doesn't necessarily happen with a crossbar. With a crossbar, if you're communicating to different pairs of nodes, if node 111 is communicating to memory 111, and node 001 is communicating to memory 110, there's no contention in the crossbar. But in a network like this, there's contention. Right? And somehow you need to handle that contention. You get this delay that's not present in a crossbar. Make sense? That's the downside of this indirect network. And somebody needs to handle that connection, conflict. The question is who, right? So there are 2 methods of handling that conflict. One is you can pre-schedule or pre-allocate these links to the communicating nodes, the sender and the receiver. Let's say the sender 111 tells the network that I'm going to send a bunch of messages to receiver 111. Reserve this path for me. And the network somehow knows that there's a reserved path. How can you do that? Basically, you can set up reserved paths in each switches. Each switch has some memory, and the switch says this path belongs to this input. And later, if 001 wants to communicate to 110, it also asks the network, asks all of the switches, I want this path. And this, when the request comes to the switch can say, no, you cannot have it. At least you cannot have my path here. Because somebody already is transmitting requests. Because they asked me to reserve this path to send from 111 to 111, right? Processor 111 to memory 111. So that's called reservation-based scheduling. Or another word for this called circuit switching. You may have heard of this. Have you guys taken a networks course? Not yet, at least. So this is called circuit switching in a network. Basically, you set up the full path and reserve it. Set up the full circuit and reserve it for a pair of communicating nodes. And no one else can use it. The alternative is packet switching. You don't have this reservation, but now router is more complicated. Router needs to arbitrate between these requests. When you set up the path, when you do circuit switching, you can basically set up the muxes such that this router always communicates this input to that input, right? And that's lower latency. It may not be that big of a deal when you have 2 inputs and 2 outputs, but if you have 6 inputs and 6 outputs, that crossbar that you have or something that you have within that router, if you set it up, if you set up the muxes and ensure that that setup does not change, the latency is much lower. Does that make sense? By the way, that reminds me of something. If you look at this network, this is the Omega network, right? Let's assume that it's not the Omega network and you have a bunch of inputs here. Let's say this is a router that is 10 input and 10 outputs. It's very similar to the external thing, right? You could actually do the same thing inside the router as well. Inside the router, you could partition the router to smaller networks. So the components of a network is very similar to the outside networks. This is also called self-similarity. So the components, subcomponents of the system is very similar to the bigger components of the system. You can build the overall system with components that look almost exactly like the system itself. Because you need to have a router here that needs to route maybe 8 inputs to 8 outputs. Not in this case, but OK. So this is a circuit switched version of the network. You can have in this case, you can have a 2x2 crossbar for each of these links. This is very similar to what we had here. And we already talked about this. We already talked about the fact that this has more restrictions on which transaction, which node can communicate with which other node, because you need to actually reserve a path. If you reserve a path, you're basically blocking some other communication. For example, if 7 to 7 was reserved, and maybe 6 to 6 was reserved, this 0 cannot communicate with 7, right? Because you're circuit switching, because you've already set up the paths. But now you're more scalable still compared to a crossbar. The packet switch network, when you have packet switching, you somehow need to arbitrate, right? Basically, packets hop from router to router, and pending availability of the next required switch of the buffer. And the router itself arbitrates. So you dynamically select which packet should go to a link instead of reserving the route. So this is a lot more flexible, of course, right, with packet switching. The downside is the routers are more complex, right? And it's higher latency. So circuit switching sets up the full path. You establish the route and then send the data. Packet switching routes per packet. Well, obviously no one else can use those links. And route each packet can be routed possibly via different paths also. If the link is free, any packet can use it. The upside I already told you, faster arbitration. The downside is you need to set up and bring down the links. And that takes time. If you look at internet, you can have ATM networks. And those suffer from setting up and bringing down the links. You can communicate through the entire internet this way. Internet doesn't operate this way today. It's not packet switched. It's not circuit switched. It's packet switched, right? You don't send out, reserve a path from here to Google. There are routers that actually route different packets of everyone. And that's much more flexible, right? So packet switching is potentially slower because now you must dynamically switch. For every packet, you need to decide where it goes instead of for a sender transaction pair. There's no setup or bring down time. That's the upside. It's more flexible. We've already talked about it. It doesn't underutilize links. So that's if you actually set up circuit switching and the sender is not using the circuit and it's not bringing it down, you're underutilizing your links. Right? Okay. So this circuit and switching, circuit versus packet switching, this choice is independent of the topology. Right? It's a higher level protocol on how a message gets sent to its destination. But some topologies are more amenable to circuit versus packet switching, and I'll let you think about that. Actually, that's fun to think about. It's always fun to think about these interconnection networks because they're everywhere, right? Okay, another example is the Delta network. This is actually one of the earliest interconnection networks. This is also a paper by Janak Patel, who was the inventor of the MEZE coherence with a student. And this is the network he had envisioned at the time. It's very similar to an omega network, except I think all pairs may not be possible. But yeah, exactly. It doesn't support all possible permutations. And you can figure out what permutations are possible and are not possible. So its cost is a little bit lower than the omega network. And the idea was the same, though. It was proposed to replace costly crossbars as processor to memory interconnect. You have these processors here. You have these memory banks here. How do you connect them? And all of the discussions that we had on DRAM, we assumed a single bus, right? Connecting the memory controller to the memory banks. They don't need to be that way. It can be this way also. Today's DRAM interface requires that single bus. Again, it doesn't need to be that way. Okay, this is the omega network. You have, again, very similar to the Delta network, except now you have all stages are the same. If you look here, all stages are not the same. The connection from here, you go to the bottom one here. You go to the top one here and the one below here. Here you're shifted. You go to 1 below and 2 below. And then you switch back. So it's symmetric across the x-axis, I guess. Here, all stages are the same. If you look at this, it's the same, right? Well, I guess except for the top part. You have nowhere to go over here. OK, this is used in the NYU Ultra computer. And this was one of the scalable machines of its time. And one other thing that they did in this computer, actually, I'll just give you the idea. They had some operations in the router. Here, I told you that this router does nothing but just routing. But what they decided to do is to have some operations on the router as well. So if multiple processors are incrementing a variable, what this router could do is was to aggregate those increments. If it receives an increment request, which they could do, and a request from this processor, and another increment request from this processor to the same memory location, the router could detect that and combine those requests. These are called combining operations in the network. And that would reduce the latency of updates to shared data variables. OK. I guess one thing we have not covered is the ring, right? This is the now we started that we'll approximate the crossbar, and this is how you approximate the crossbar with a less costly network. But if you want to scale up the bus, well, the next thing is a ring over a bus. And a ring, you already know what a ring is, right? Basically, you have point-to-point connections between processors that are adjacent to each other. And I guess these are not necessarily adjacent to each other, but you could make it adjacent to each other when it looks like a ring. So this is cheap. It is ON cost. The downside of this is it's high latency. Right? If a processor in the middle needs to communicate with a processor on this other end, then it needs to traverse half of the ring. It's not easy to scale also. Bisection bandwidth remains constant. We didn't talk about bisection bandwidth, but one of the evaluation methods of a network is you cut the network in half where there are the most connections and look at the bandwidth. Look at the throughput that is supported across that. That's your bisection bandwidth. And that determines how much transfer you can sustain across the network. You don't need to know about that. That's one method of measuring the performance of a network. That's not the best method because in the end, system performance is what's important, right? It's not, you're not measuring the network in isolation. That's the downside of this kind of metric. So it's not easy to scale, basically. Why is this interesting in this case? Why is bisection bandwidth interesting in this case? As you add more processors to the ring, you're not really adding anything, any more bandwidth to the network, right? Whereas as you add, if you have a point-to-point connection, for example, as you add more processors, you're really adding more bandwidth to the network, right? Because you need to add another point-to-point connection. Or as you add more processors to a multi-stage network, again, you need to add more bandwidth to the network. So this is actually used in many small-scale multi-core systems today. Intel systems use it. IBM Cell that we've discussed last time uses it. And you can have a unidirectional ring or bidirectional ring. And ring routers are simple. The upside of a ring is it's very simple, right? The router looks like this. This is basically how you inject into the network. This is how you eject from the network. And that's it. And it doesn't have to have buffers, again. It can be bufferless. OK. Basically, you get reasonable performance if n is low, the number of nodes is low, and your cost is low, but the latency is high. And latency actually depends on utilization also. Mesh is a little bit more scalable than the ring. Its cost is still ON, so it looks like this. Basically, you're connected. It's a two-dimensional network instead of one-dimensional as the ring. Now you're connected to your immediate neighbors. The average latency in this case is the square root of n. It grows with the square root of n. And I'm going through this relatively quickly, but you can imagine these things, right? And the upside of this is easy to lay out on chip. It's regular and equal lengths, right? The other upside is you have path diversity. There are many ways to get from one node to another node. Right? It's not as good as the crossbar, but it's much better than the ring. Right? There's only one way from, well, if you have a unidirectional ring, there's only one way from getting, for getting from node 0 to node n minus 1. If you have a bidirectional ring, then you have two ways, right? With a mesh, you have a bunch of ways. Perhaps you can calculate how many ways. Right? So that enables a lot of concurrent transfers. So this is actually used in a commercial system, Tyler, as embedded processors that have 100 cores use this. And many on-chip network prototypes. Now the downside here is the routers are more complex. Right? It's a 4x4 router for this case, whereas a ring router is 2x2, much simpler. A torus, the downside of mesh is one of the downsides is the edges are not symmetric, right? If you want to go from this node to this node, you actually need to go all the way this way. But if you had a connection here, wouldn't it be nice? That way you would have one hop. And that's the idea of a torus. So because the edges are symmetric, you can get a lot of contention around these areas if you don't map your data nicely. Because there's nowhere to go, right? Whereas here in the middle, you have a lot of flexibility in routing. Whereas here, you don't have much flexibility. So torus solves that problem by making mesh more symmetric. Basically, you're symmetric on these edges. So you get rid of performance sensitivity. If you place a task, the performance you get is not dependent on the network, right? Because every node is the same. So that makes scheduling tasks on this kind of network much easier, because the operating system or whatever scheduler you're using doesn't need to reason about, oh, should I place this task on the corner? What are the performance characteristics of this task? Will it be stuck there? Right? Torus avoids that problem. You get higher path diversity and than mesh. The downside is, of course, higher cost. And it's harder to lay out on chip because you have unequal link lengths. I guess the question is that true? Can you guys imagine a way of laying this out on chip such that you get almost equal link lengths? Yeah? No? You can think about it, and actually you can do it. You can weave the nodes to make internode latencies almost constant. It's not perfect, but this is actually a torus. This is just one direction of it. You can see that this is actually a torus. Okay? So trees are another network, and this is actually used in many supercomputers. This is an H tree here. You have a hierarchical topology, basically. And tree is a tree, right? You could have a binary tree. In this case, I guess this is a quad tree, right? You have 4 nodes connected. And you could have more nodes connected to this. The latency is of log n, which is tree height is determined by log n. And the base of the log is actually how many, whether you have an n-ary tree. This is good for local traffic, right? If you have a tree like this, if these nodes are communicating a lot with each other, it's easier to communicate. And this is another tree. Ignore the fat part now. Let's assume that the links are the same. It's another tree, right? If these two nodes need to communicate with each other, they just need to go through this router. This is good for local traffic. Right? If you map your data nicely such that the communicating nodes are here, that's great. So we have fat trees here as an example. The idea in a fat tree is as you go above, as you get closer to the root node, your bandwidth, the links become wider or higher frequency. The bandwidth increases. Why? You want to satisfy the communication. The assumption is that the communication that occurs here is uniform. And if the communication is uniform across all levels, you want to satisfy that communication at the high level also. So it's cheap. So overall, these are cheap. The cost is ON again. And these are actually easy to lay out if you're regular. For example, this is not too bad to lay out. If you think about it, clocks are designed that way. If you do clocking in a processor, a clock, you can have an H tree for the clock signal. Right? That's how the clock goes to the nodes. Here you can have an interconnect the same way. Right? A clock is no different from an interconnect, except you don't have switches. The distribution of the clock. This is actually the clock that goes up and down, right? It controls your synchronous circuits. That's essentially usually designed as a tree today. That's the clock distribution tree. We're not talking about that kind of interconnect, but we're talking about another interconnect for communication. If you can lay out the clock, you can lay out this one as well. The downside is root can become a bottleneck, right? If you have a lot of communication over here, this can become a bottleneck. And that is solved by making the tree fat. And fat trees were employed by the connection machine 5, which had lots of processors. And this is the CM5 fat tree. Basically, you have this fat tree based on 4x2 switches. And you can see 4 inputs, 2 outputs. And they used randomized routing on the way up. And they had actually these operations that I talked about, combining operations. And they had multicast operations. They could multicast a signal to a set of processors. And they had also reduction operators. What is a reduction operator? Basically, they could do additions, they could reduce things here. So one example I'll give you very quickly is, let's say you want to add a bunch of numbers in an array. What you could do is you could distribute the array across the nodes down here. And this node can add the first 2 elements of the array and send the addition up. This node can add the next 2 elements. This node can add the next 2 elements. This node can add the next 2 elements. And all 4 sums go to this node. And this node can have some capability in it that adds those 4 numbers. Right? And then it can transfer the sum to the node that's higher. So this way you can get an addition of the entire array very much in parallel. Right? And that kind of computation fits nicely in a tree. Make sense? That's beautiful. If your computation fits nicely with this kind of communication substrate, you can get very, very high performance. The difficulty is, can you actually make your computation fit nicely with, on top of this kind of substrate? Okay, I guess we're going more and more, but Hypercube is another kind of interconnect. And I'll let you look at these calculations, but this also has nice latency characteristics and number of links as well. Radix is basically how many nodes a router, how many links does a router have? And these are, you can go up to 4-dimensional hypercubes here. And you could actually go more. And I guess I'll give you a number. The upside is low latency, right? You have nice low latency in a hypercube like this. The downside is hard to lay out. How do you lay something like this out, right? Actually, it was done. Caltech had the Cosmic Cube in the early 1980s. It was a message passing, actually one of the first message passing supercomputers. And they had a 64-node machine, which looked like this. Right? This is a binary 6-cube or 6-dimensional hypercube. And this is two-dimensional projection. It was not two-dimensional, obviously. Right? These were actually big nodes. It's not like a multi-core system that you have today. And that's how they connected these things. And these are the processors and the switches. It's another way of looking at it. Okay? Okay. One key question. We're done with the topology, actually. You can imagine many other topologies, but I just want to give you an idea of what people have thought about. And there's a lot of trade-offs associated with this. One other trade-off in a network is how do you handle contention? And I'll briefly cover this. When two packets try to use the same link at the same time, what do? And we've seen several ways of doing it. Anybody who wants to take that? You can buffer them, right? If you two packets, one packet going from this direction, another packet going from, I guess here you cannot see, but let's say you have one packet going from this direction, it wants to go to this way, coming from this direction, and that wants to go to this way. They contend for this output port. What do? You can buffer one, right, and let the other one go. What else can you do? I guess not buffer one, or not buffer anything. And that's actually a valid design point also. If you don't buffer any of them, and one of them wants to go this way, both of them want to go the same way, what do with, you grant this way to one of them, what do with the other one? Well, yes, you can drop them, right? You can drop that. That's one option. What else? Huh? When you drop it, yes. When you drop it, you need to somehow send a negative acknowledgement so that the source, the sender, needs to know that it was dropped. But let's say you don't want to drop it. That's right. You can route it to another direction that it doesn't it doesn't want to go to, right? So these are three fundamental options. You can buffer one, drop one, or misroute one. It's also called deflection. You deflect one to some other location, some other link that's free, basically. And you can do that as long as the number of inputs, number of output links that you have is greater than the number of input links, greater than or equal to. And these have actually, now you run into trade-offs, right? Buffering one requires buffers. Dropping one, now you don't necessarily need to have buffers, but now you need to have negative acknowledgements, right? Misrouting one, now you have perhaps additional latency. You'd have additional latency with dropping one also. But you don't need buffers and you don't need negative acknowledgements. You somehow need to, eventually, the hope is that once you misrouted this packet, it'll come back and go some other way in the network, assuming your network has that property, right? Your network needs to have that property. So that's a very interesting choice that you need to make, and I'll let you think about the upsides and downsides. And the upsides vary from complexity, latency, as well as energy, right? How much energy do you need to use? So I'll talk a little bit about bufferless deflection routing, because this is an area that we've been very interested in the past few years. This is actually a very old idea. It was proposed for communication networks by Paul Baran in the seminal report that was published in IEEE Transactions on Communications. The idea is you never buffer any packet in the network when two packets contend for the same link when it's deflected. So if you look at a mesh like this, let's say two packets need to go to that destination. They arrive at this router. This router can grant that output to only one of them. Well, it picks the red packet and it sends the blue packet to some other node. And blue packet eventually makes its way to the destination, right? So it can work. So blue packet traverses a little bit more, but now you get rid of the buffers and the complexity of the buffers. You don't need to have a flow control mechanism that that ensures that the buffers do not overflow. You just need to have a mechanism that ensures that the links do not overflow in the system, right? Because now you're actually using the links as your buffers, in a sense. Because if this link is free, why not send the packet there? There's a link. So new traffic can be injected whenever there's a free output link. If this processor is going to inject to the network, all of the output links need to be free. Okay? So if you look at this, this is a router, and I'm not going to go into this in detail, but this is a 4x4, I guess 5x5 router in a mesh. You have 4 directions, and you have the local input and local output also. Normally, you have these input buffers, and you have arbitration mechanisms for the switch, which is a crossbar. And this arbitration can be complex. As you increase the number of inputs, your arbiter becomes more complex. This is essentially what you've seen, right? This 4x4 thing is really a network also internally. It could be a multi-stage logarithmic network here. Input buffers now can be eliminated, right? Flits are buffered in the pipeline latches and the network links. So deflection routing logic is simply this. But of course, it's not as simple as this, so we can talk about that later. OK, let me briefly cover the routing algorithm. I'm going really fast, but I want to give you a very brief overview. And if you're really interested in this, you should really take the next course. But routing algorithm is very important also. You can have 3 types of this. It can be deterministic. Basically, it always chooses the same path for a sender-receiver pair. Right? Always the same path. It could be oblivious. It can choose different paths, but it doesn't consider the network state. It can be adaptive. It can choose different paths for the sender and receiver pair, but now it considers the network state. If the network is congested at some point, you route somewhere else. Right? And this is the most flexible one, obviously. And how do you adapt is another question. Right? How do you figure out the network is congested? Let's take a look at a couple of examples. In deterministic routing, as I said, all packets between the same source-destination pair take the same path. One example is dimension order routing. If you have a mesh, you could do XY routing, for example. The idea is if 2 processors are communicating, and this is your mesh, if this processor needs to send a message to this processor, first, the packet is routed along the X direction, and then when it reaches the Y direction of the destination, it's routed around the Y direction. Or you could have YX routing, right? It could be first routed toward the Y direction and then toward the X direction. So you have an order between the dimensions, and you follow that order. Simple, very deterministic, right? And because of that simplicity, it was used in Cray T3D, which was a supercomputer, which was in the top 500, or top of the top 500 at some point, I believe. And many on-chip networks actually today use this. So the upside is simple. It's actually free, deadlock-free. We're not going to cover this. Actually, we will talk briefly about it. The downside, it could lead to high contention, right? What if all of these processors are actually sending requests to this destination here? All these 4 and maybe all these 3. Well, you have lots of contention on this link, right? Even though you have lots of path diversity in your network. You could have gone somewhere else. So it doesn't exploit the network really well. What is deadlock? I believe to talk about this. But if you actually have buffers in the network, deadlock is no forward progress. Right? And when you're designing these networks, you need to keep this into account, take this into account. What may happen is you can have circular dependencies on resources. And here I'm showing you, I believe, 4 routers. And what's happening is each packet is waiting for a buffer occupied by another packet downstream. This packet 3 is waiting for a buffer that's occupied by packet 4, that's waiting for a buffer that's occupied by packet 1, that's waiting for a buffer that's occupied by packet 2, that's waiting for a buffer that's occupied by packet 3. You can examine this figure. And you don't want this in a network, obviously. So how do you get rid of that? There are 3 fundamental techniques again. You can avoid cycles in routing. Basically, cycles in routing happens if a packet can actually go this way. Right? Here, with XY routing, you never can have a cycle. You cannot build this circular dependency. And I'll let you think about that. If you have dimension order routing, you cannot build this circular dependency. Because all packets need to go X direction first and then Y direction next. You can restrict the turns each packet can take. That's what is happening with XY routing, basically. Or you can avoid deadlock by adding more buffering. Right? You can ensure that this never happens by adding escape paths. Or you can detect and break deadlock. And this is the harder one. How do you detect these cycles? OK, I'll skip that. Oblivious routing, an example of this is actually a very commonly used algorithm, variance algorithm. The idea is you don't want to be deterministic. You want to choose your path in a way that exploits the diversity in the network so that you don't run into these contention situations. But when you're doing that, you want to be simple. So the idea is you want to balance the network load. With variance algorithm, the way it's done is you can divide the network into something like this, quadrants. What you can do is, if this node is going to send a message to this node, it first finds a random node in the network, randomly picks a node, and it routes the message there. And then from this node to this node, message is routed maybe with XY routing. Make sense? So the goal is to balance the network load here. If all of the nodes are communicating this way, eventually your pattern randomizes, right? Your pattern is kind of random. It's beautiful. Okay. So it balances network load. Of course, there's a downside now, right? Your latencies can be very long, right? If you choose a node randomly. It can be non-minimal. Packet latency can increase. And if you don't have much contention in the network, balancing the network load may not be a good idea. Because you're not going to run into contention anyway. Why not send the request through the fastest path instead of going through an intermediate node that makes it longer? Okay? So you can optimize this. You can do this only on high load when there's lots of contention in the network. Somebody needs to detect that, of course. And you can restrict the intermediate node to be close. So if you can say, I'm going to randomly pick a node within the same quadrant. Or I'm not going to randomly pick a node that's here, for example, because if you pick a node, intermediate node here, it increases the distance, right? You could do that kind of design choices to reduce the latency impact of this. And finally, the most flexible algorithm is routing mechanism is adaptive routing. And adaptive routing basically adapts the route that's chosen to the state of the network. Oblivious routing is oblivious of the state of the network, right? We randomly pick a node. We don't say, oh, let's take the not congested path. Adaptive routing, we take the not congested path. That could be one way of choosing the path. Router uses network state to pick which output port to send a packet to. And this output port, it's called productive output port here, is the port that gets the packet closer to its destination. Right? This is minimal adaptive. So you can actually do this minimally. Minimally in the sense that you don't increase the latency of a packet. There's some minimal latency from going from here to here. The minimum latency you can have is 1, 2, 3, 4, 5, 6 hops, right? Or you can count that, I guess. I guess in this case, 1, 2, 3, 4 hops. But I'm missing a node here. 4, 5 hops. Non-minimal means you always keep this. Minimal means you always keep this minimal latency. So you always choose a productive output port such that you minimize congestion. And you have this choice if you have multiple output ports that are minimal. So for example, if a packet is going from here and it needs to go here, it could go this way, which is minimal. I guess, can it go another way? Yeah, I guess it could go this way. That's minimal, right? That's the same number of hops. So you have a choice. You could take the not congested path if you know what's going to happen later on. Right? Okay, the upside is this aware of local congestion. The problem is now minimality restricts achievable link utilization, which means that you cannot take this packet and send it this way, right? Because that will increase the latency of the packet compared to the baseline latency that it could have. So if you have non-minimal adaptive, it's actually bufferless, like deflection routing. Basically, you can now misroute the packets to a non-productive output port. Non-productive output port is an output port that increases the latency of the packets. Now you're more adaptive. You're still adaptive because you think that there's some congestion here, but you cannot route the packets here because these links are busy. So route the packet to a non-congested area. But that non-congested area increases the latency of the packet. This could be OK, right? Because now you're utilizing links in your network. So you can now achieve better network utilization and load balance. The downside is somehow you need to guarantee live lock freedom. Now you can think about this. What is live lock? If a packet keeps circling around in the network, never reaching its destination, it's live locked. Right? It could happen if you're non-minimal adaptive, because you're sending a packet to a direction it doesn't want to go to. And you need to have mechanisms to prevent that. OK, I'll briefly cover this, but these interconnections are actually in today's multi-core systems. And the same scalability problems that were faced by supercomputers are being faced by today's multi-core systems. If you look at a multi-core system, you can have an on-chip network, on-chip interconnect, this is a mesh interconnect, that connects cores, caches, memory controllers, etc. In this case, you can have processing elements, which could contain a combination of any of these, cores, L2 banks, memory controllers. And they're connected via these routers or switches that communicate, enable communication within the network. And buses and crossbars are not scalable if you want to increase the size of this. And point-to-point networks are obviously not scalable. So it could be packet switch network, and 2D mesh topology is commonly used, this kind of topology today. But that's not necessarily the best topology again. With smaller scale multi-core systems, rings are used. And today, these primarily serve cache misses and memory requests. The Tylera chip has 5 different mesh networks like this for different kinds of traffic. Some of them contain just the I/O traffic. Some of them contain streaming traffic, and it's a circuit switch network. Some of them contain cache miss traffic. Okay, and actually, this interconnect consumes significant power in today's systems. And these numbers, take these with a grain of salt. Some of these are actually unoptimized implementations. For example, the raw prototype, which is very old right now, from 1990s. Intel's terascale prototype had about 30% of the chip power consumed by the routers and the interconnect. But again, that was probably not optimized. And Intel's single chip cloud computer, which also had a mesh interconnect, had about 10% of the power, system power consumed by the interconnect. So we need to make these more, going forward, we need to make all of the system components energy efficient, but also interconnect the energy efficient also. I think I'll stop here. I promised that I will finish early, and I did finish early. Any questions? So hopefully this gives you a good idea of what a parallel computer architecture looks like, and what you need to do if you want to scale it. Okay. And if you're really interested in this, you should really take the next courses in sequence.